Let's talk about a question I had when I was a student. We talked for a very long time about the trapezoidal rule, the Simpson rule, the Newton-Cotes rules, and the Gauss formulas, the Gauss quadrature formulas. And all these ideas, the ideas behind these algorithms, are based on the principle we want to integrate polynomials exactly, and we want to have high degrees of these polynomials. But why? Why do we try to be exact for polynomials? What is that good for? We don't need numerics for polynomials. For polynomials, you can easily find the antiderivative, and then you can integrate as you learned in Mathematics 1. We always prefer algebraic methods and we never prefer numerics. So why do we try to solve problems numerically which can easily be solved without numerics? That was my question. We need formulas which work for functions like that. Exponential of minus x squared. This is a function you can't find the antiderivative in an algebraic version. So here you need numerical ideas. But in this case, our formulas are not exact. Why don't we try to be exact for functions like that? That was my question, and I did not find a satisfying answer in the first moment. But the answer is not very hard. The crucial point is how good are the interpolating polynomials. When we apply the trapezoidal rule, Simpson, Newton-Cotes, then implicitly we integrate the interpolating polynomial. So implicitly, the first step is find a polynomial which interpolates the function values and then integrate this polynomial. That's not the way we do. We found a way which is much faster, but implicitly, exactly this is what's going on. And so the question is the polynomial a good approximation of the function or not? If the polynomial is very close to the function we want to integrate, then the integral values will be very good. If the interpolating polynomial is far away from the function we want to integrate, then the integration values we find by applying Newton-Cotes are bad. So let's illustrate that with that integrand, exponential of minus x squared plus 2x, and then we integrate from minus 3 to 3. The correct value, I found that value, is 4.8068. And now let's work with Newton-Cotes formulas of degree 3. And then we see the following. If we don't split the integration interval, we have one interval, then we will evaluate at the first point minus 3, at the end point of the interval plus 3, and 2 points in between, which are minus 1 plus 1. And then we evaluate, we get these 4 values, and then implicitly the interpolant is calculated, this one, and then here is the x-axis, this area we find. But we are not interested in this area between the x-axis and the red function, but we are interested in this area. And so because there is a big difference from the function and the interpolant here especially, then we have a very bad approximate value. So seeing this picture, you will never see that picture if you apply the formulas, but seeing this picture, it's clear that if we apply Newton-Cotes degree 3 and without splitting, this value is a bad guess of the true value, and the value is 6.2655 instead of 4.8068. So a very, very poor result. But seeing that plot, it is clear. Okay, if we split the interval, then we have here -3, 3, 0. And then we evaluate at position -2, -1, and 0. And then with these four values, we can find the polynomial interpolant of degree 3, and we see it's very good. The red curve and the blue curve is very close together. On this interval, we evaluate at 0, 1, 2, and 3. And here we see the red curve is okay. It's much better than it was here, but there are differences. So the integral value will be not a perfect one, but better than the left one. And indeed, the integral value is 5.0081 instead of 4.8. So if we refine one step more, then here we have -3, 3, 0, -1.5 and +1.5, and then we evaluate here these 4 points, and there's no difference between the blue curve and the red curve. Optically we see no difference. Also here very slight difference, and here no difference. So it's clear, if we split the interval in 4 parts, and then on each part we apply the Newton-Cotes formulas of degree 3, the integral value is quite good. And indeed, our integral value is 4.8130 instead of 4.8068. So if we want to have even the 4th digit after the decimal point correct, then we have to do further refinement, and then you will see no difference at all. And to be really that exact, you need a good refinement. So if you want to understand integration, then you have to think about interpolation with polynomials, and the better they are, the better the integration is. And I recommend, please feel free to reproduce these 3 values. That is a simple call, having my MATLAB routines, which I give you. Having these routines, please try to recalculate these values, and maybe you can also reproduce the plots, and that will be a good training for you. So we completed the discussion about this question.